11 a.m. and it's time to continue. So first of all, this is going to be the long weekend. Yesterday, somebody reminded me. It means that Monday is the holiday, and then on Tuesday, we're going to have Monday's schedule. So we're not going to have a lecture on Tuesday. Right? So after this, the next lecture will be in a week. And I think that is the due day for the second homework about the energy, right? Which is homework number 4, right? And most likely, a week after that, we will have, around that time, we will have the first midterm exam. Okay, so that's about the organizational questions. And now back to the stuff which we started discussing in the previous class. So what was it all about? Before that moment, every time we had systems, systems exposed to an external conservative force. As a result, we could introduce sort of an external potential energy, right? So potential energy, which comes from an interaction of an system, of an object, your system, with the object which is outside of the system, right? And we developed all those energy tools. And then we decided, but what if our system is isolated? So there are no any external objects. And that system of two particles, the system interacts through a conservative force. Right, so now internal forces are conservative forces, right? And so we ask ourselves the question, so can we introduce potential energy in this case? So again, so we have interaction, interactions through a conservative force, so it makes sense to assume that it's possible to introduce potential energy. And without a derivation, I justify why I don't do the derivation anymore, we just introduce, so yes, it's possible to introduce potential energy in this case, and that potential energy will be a function of a relative position vector, R1 minus R2, which is just basically vector defined position of one particle relative to the other one. And then, so of course, there are two forces between these two objects, right? Because they exert forces on each other. So F12, it's a force acting on the particle 1, and the force comes from the particle 2. So in order to find that force, we just need to take a negative gradient with respect to the coordinates of particle 1. The force is exerted on particle 1. So gradient with respect to the coordinates of that particle. Of that gradient of that potential energy, not just potential. Since I had in the morning lecture physics 2, still sometimes the terms from that class pop up in my head. Potential energy, right? And then, of course, exactly the same with the force F21. But now, of course, we need to take a gradient with respect to the coordinates of the particle 2, right? Okay, so that was in the previous class, right? Again, without a proof. And then we decided, okay, so now we have two objects. Of course, definitely we can introduce kinetic energy, two kinetic energies. And so now, can we get total mechanical energy? And will it be conserved? So logical question. So now we have potential energy, kinetic energy, definitely kinetic energy. So can we get naturally total mechanical energy and see if it is going to be conserved? Right. Again, where should we start? From the whole energy approach was, we started from the Newton's second law. From the Newton's second law, we got work kinetic energy principle, just simple massaging. Okay, not so simple, but massaging, right? So we got work kinetic energy principle. So this is basically universal, right? So you can apply it for any, and again, it was derived for point mass. But we do have point masses, so it means that we can apply this for this point mass and then for that point mass. Work kinetic energy principle has no restrictions like Newton's second law. Right, so we wrote down a work kinetic energy principle or theorem for the first particle, So if you have particle 1 which moves along this trajectory and particle 2 which moves along that trajectory, right? So of course, change in the kinetic energy over infinitesimal small displacement equals to the work done by this force F12, right? So F12 dotted with dr1. So it's that's how we can apply work kinetic energy principle for the first particle. And then exactly the same for the second one, but now of course we have to deal with the force F21 acting on particle 2, which comes from particle 1. So that's where we ended up in the previous class, I think, right? So and now we can continue, right? So since we have now a system of 2 particles, so it makes sense if we want to look at the total mechanical energy, let's add them up. So as a result, of course, we ended up with change in the total kinetic energy, which is dt1 plus dt2, and it is equal to this. Or we can say, let's look at the total work done, but it's better to say change in the total kinetic energy. So it will be F12 dotted with dr1 and plus F21 dotted with dr2. Okay, so now let's start using the assumptions which we imposed over here. That what if which assumptions we imposed over here, right? Okay, without derivation, that these forces, first of all, conservative, second, central, and obey Newton's third law. And it happens quite often in most of the systems which we see in classical mechanics, because usually those forces are what? Force of gravity and electric force. Yeah. Okay, so at this point, let's use the fact that these forces obey Newton's third law. So let's assume they obey Newton's third law. So basically F21 equals to minus F12. Okay, so now, of course, we can factor out F12. Of course, I will keep F12, get rid of F21. So we will have F12 dotted with, and it will be dr. Yeah, let me immediately skip step. So it will be dr1 minus dr2, but I can take differential outside. It will be differential d of r1 minus r2. dr1 minus r2, right? Okay, now it's time for the next assumption, which we assumed at the very beginning. So these internal forces are conservative. F12 and F21 are conservative. So as a result, we can use this. Okay, actually the first one, since I decided to keep F12 force. So it will be minus gradient taking with respect of the coordinates of the first particle. So it will be, okay, let me just write. So it will be minus gradient with respect to coordinates of the first particle, u of r1 minus r2, right? Okay, conservation of brackets, and dotted with dr1 minus r2. Okay, so of course now obviously we have relative position vector, which is r1 minus r2, right? And, all right, so let me write. So r, we can introduce r1 minus r2, so it's a relative position vector. Right, and as a result, will be, you know what, let me just again start this dt, right? Because this getting too long, so let me restart it. dt equals this. All right, so it will be dr. Let me write first this and then dr. So it will be minus gradient with respect to r1, u R and dot it with dr. Okay, now you see where I'm trying to get, right? Sort of my goal. It's getting out of this mist, right? Basically, I want, okay, let me write, we want, not just I want. It sounds too selfish, right? So we want. So what we want to actually use, right? You remember, I think it was about 3 classes ago when I introduced a gradient, right? That hybrid operator. And we wrote down that the change in the differential of u equals to gradient of u dotted with dr, dot product with dr. And so basically that's what I want to get. I want to get to this structure, to this shape, so that instead of this construction, I can write du, differential of u. But where is the trouble? So for now, in what we want, this gradient is taking with respect to r the same r as here in this differential. But in our construction is not ready to be transformed for using this, because what we have here dr, relative position vector, but gradient with respect to r1. Damn it, not completely ready, right? So we need to do something with this expression first before we can transform it using this expression and transform it into du, right? So basically we need to, okay, let me emphasize what is still wrong. So these are, okay, let me emphasize, these are the same, right? But in our case, R1 and R, these guys are different. And so now let's look at this gradient. I'm just trying to estimate, should I move to that side? Okay, maybe I still will be able to squeeze a little bit more. All right, so let me write, so what do we have here, this gradient? So gradient with respect to r1 out of u, which is a function of r. Of course, it's a what? In a component form, it's a x hat du over dx1, right? Because we're taking gradient with respect to the coordinates of the first particle. So this coordinate x1, y1, z1, right? Then plus y hat du over dy1 and plus z hat du over dz1. Okay, so now let me look just at d over dx1. Okay, now it's time for me to move here. So d over dx1, partial derivative with respect to x1. Of course, I can make this transformation. I can write so d over dx, dx over dx1. Again, what is x? X is a coordinate of this relative position vector. So x, y, z, right? So that's what that x is. Okay, let me remind it. So r is r1 minus r2. As a result, of course, x equals to x1 minus x2. And our partial derivative, dx over dx1, dx over dx1, since it is a partial derivative, the rest of the variables except for x1 we treat as a constant. So it means that dx with the derivative with respect to x1 out of x2 is 0. So that is just 1. Okay, let me extend this explanation box. Okay, it looks ugly a little bit, but functionally better. Okay, so this is 1. As a result, it's just d over dx. So similar, of course, similar we can do, Similar, we can talk about y and z. We can say exactly the same about y and z. So similar, d over dy will be equal to d over dy, and the same about z. So as a result, I can write so that gradient with respect to r1 will be equal to the gradient with respect to r. So not much of a transformation to our equation. We just need to drop subscript 1. Right? So as a result, let me rewrite this over there. Right, dt equals minus gradient with respect to r, u as a function of r, right, and dotted with dr. Okay, and now it's completely legal from the mathematical point of view to use that. Okay, so that is equal now. Right. Okay, so now let me emphasize. So now again, r, and they're the same. So now we can write that it's equal differential of u. Okay, so cool. Now I can, of course, minus. I was so happy that now we can write differential, so I forgot about the minus. That minus is still there. It doesn't go anywhere. Okay, so now we can write d. And of course, what is T? T, it's a total total kinetic energy. So which is T1 plus T2. Right? So now we can write T1 plus T2 plus U equals to 0. So this quantity, it looks like, is conserved. So T1 plus T2 plus U. And so, of course, we are going to give it name total mechanical energy, T1 plus T2 plus U. Right? Of course, it's a function of R. And E is constant. Yeah, conservation of mechanical energy. As it should be. So we are getting that it can be used as well. Of course, assuming that we don't have losses. But of course, there are no losses because the system is isolated. It doesn't interact with anything which is external to the system. So, and losses, of course, will come from an interaction with external objects. So, what's next? Yeah, of course, I need to frame it. And yeah, so we have two kinetic energies because there are two objects, and only one potential energy because, again, potential energy, it is an energy of interactions, right? So you must have at least two objects to have interactions. Okay, so where that can be used? Billiard balls, elastic collision, for example, right? So during that, okay, I don't have billiard balls, I have tennis balls, right? So during the interaction, these forces of interactions are conservative forces, usually in the case of an elastic collision. So in that case, there are any losses, right? And if kinetic energy gets transformed into potential energy, then potential energy is transformed back into the kinetic energy, right? So during the elastic collision, energy is not conserved. And again, forces of interactions are conservative forces, right? So basically, all this is applicable. The only difference here, of course, these forces kind of distant forces, they act over long distance. But in this case, force acts between object basically only during the contact, right? And then once r increases, the relative position vector. Somewhere here, right? If r increases, of course, the force and potential, of course, decays very, very fast. Right? It basically disappears very quickly. All right, so let me just write a few lines about this. Right, application of all this for an elastic collision. And then we will look at one example very quickly. Right. And after that, rigid body, and we'll move from this chapter. Yeah, we spent quite some time on this chapter. All right, so okay, let me put a new bullet and write all these can be applied to describe an elastic collision. To describe elastic collision. Right. Basically, a collision of objects where there is no loss of energy. Okay, I can draw something like this. Let's say we have this, let's call, has kinetic energy T1. This has kinetic energy T2, right? Again, forces of interactions are conservative. Because there are two of them. Right. One particle on the other one and the other particle on the first one. Forces of interactions are conservative. Of course, central. Obey Newton's third law, all that stuff. Conservative. And of course, there are no energy losses, which I wrote, and no energy is lost. So conservation of mechanical energy can be used, right? As I said, all that stuff can be used. Right, and, yeah, so E is conserved. Okay, now let's look at the collision before collision, during the collision, and after collision in order to see what should be avoided at all costs. Right? So energy is conserved, and basically what it means you can look at the system at any moment of time, and the total mechanical energy must be the same, right? It doesn't matter before, during, at any moment of time. Right. So before collision. So let me write it as E sub B. B stands for before. Of course, it will be what? Kinetic energy of the first particle before, kinetic energy of the second particle before, plus potential energy before. But what will be the potential energy before? Because these forces are sort of short range, right? So once the particles get separated, that potential disappears. Not potential energy, again, physics 2, right? So potential energy becomes 0 during collision. So now it's the first option. Second, what about during the collision? Now, of course, collision I will skip. So during, let's say, E sub D, it will be T1D plus 2D, and plus potential energy during the collision. And of course, during the collision, they interact. Forces are not 0, and of course, potential energy is not 0. Right? So as a result, in this case, UD is not 0, right? And that potential is not that simple to model, right? Difficult to model this potential and of course these forces, right, when particles interact. Rigid objects, of course. All right, and of course after the collision, of course we can write E sub A equals T1A plus T2A plus UA. And of course after the collision, of course the last term is again 0, right? So now of course you can use any moments of time to solve the problem. And of course, because of this potential energy term, and it's difficult to model, of course, we need to, not need to, but if it's possible, of course, it's better to avoid dealing with this process during the collision, right? Because in this case, you'll have to deal with kinetic energies plus potential energy, right? So that's why every time when we describe collision, we compare total mechanical energies before the collision and after the collision, where potential energy is 0, right? So that's why it's better to avoid during. So let me write. So it's better to avoid that during option. And as a result, okay, let me remove these balls from here. So as a result, we will have what? T1b plus T2b equals to T1a plus T2a. Difficult to write over there. And of course, sometimes some students say that this is conservation of kinetic energy. Never say that. It doesn't sound cool, right? It's a conservation of mechanical energy, and potential energy happens to be 0. But it's not a conservation of kinetic energy, right? It's not completely wrong, but it doesn't sound right, right? It's just a conservation of mechanical energy in the case when the potential energies are equal 0. All right. Okay, so now let's look at the example. And I think there is a problem in your homework. Right? And this example is actually, I think, should be useful for that problem in the homework. All right, okay, I need to start erasing. I'm thinking, do I need this? No. I will erase everything. All right, so the example, collision of two particles. And collision, not a head-on collision. So during the collision, after the collision, particles will travel in different directions. So basically, it's a two-dimensional motion, right? But before the collision, one particle, let's say this particle is at rest. This particle travels. Again, not a head-on collision, right? So we need to prove that in this case, when the second particle is at rest, we need to prove that after the collision, the angle between these two particles is going to be 90 degrees. Right. In your homework, I forgot exactly the statement of that problem, but something similar. This thing looks like more like a decoration. I use it occasionally, but I don't like to use it because when I start using it, it starts erasing parts of the picture. But when you put it, it looks better. So, example. All right, so elastic collision. Right, so conservative forces acts during the interaction, during the collision, right? As a result, energy, total mechanical energy is conserved. So we can use that. Right? And okay, I will mention about that. So elastic collision of two particles. All right, masses are the same. Okay, let's assume for simplicity, yeah. M1 equals to M2 equals to M. Then V1 is given initial velocity of the first particle. Initial velocity of the second particle is 0. Right. And velocities after collision is usually, we denote usually using primes, right? Very common. So what else? Yeah, so we need to prove that the angle after the collision will be 90 degrees. Right. So we need to prove theta 90 degrees. So it's after the collision. After collision. Right. Okay, so let me separate it. And let me just quickly sketch the situation. So let's say this is particle which is at rest. So that's M2. Let's assume that this is the incident particle, M1, which moves with velocity V1. And then after collision, let's say the first particle will go along that line, so this V1 prime. And the second particle will travel along this direction. So let's say this is V2 prime. And again, what we need to show that this angle, theta, is 90 degrees. Okay, I put a question mark, so we need to show it, prove it. So that's the that's the situation. And again, system basically, okay, again, I wanted to mention that, but I wanted to ask you before I start using it. Okay, I will use. Let me start with conservation of linear momentum, and of course, whenever you use that, of course, you need to ask yourself a question. So why can we use conservation of linear momentum? Yeah, it's basically billiard balls, you can think, right? And of course, in this case, the table is designed in the way and so on, so that there are no external forces in. Okay, and now I realize that something is missing. Let me introduce coordinate system. Let's call it y, and this is x. We're dealing with vector quantities. We have to introduce coordinate system. So in this case, there are no any external forces in the x and y direction, right? Which can change linear momentum in those directions. But since there are no any forces in those directions, so we can use conservation of linear momentum in x and y direction. But I'm going to write it in a vector form because it's conserved in both directions. In z direction, who cares? But of course, even in this case, if these balls are on the table, normal force will just balance the force of gravity. So conservation of linear momentum, I can write, so M1, I used R, we're talking about linear momentum, so it's a V1, this is 0, and then M1, V1 prime vectors, plus, okay, all the masses are the same, so let me drop the subscripts. All right, M V2 prime. So conservation of linear momentum. Then, since forces are conservative, collision elastic, and mechanical energy is conserved. So I can use conservation of mechanical energy, but of course it will look like this because we're going to avoid the moment of period of time during the collision. Again, we will compare energies before with the total mechanical energy after, right? Conservation of mechanical energy, right? So I can write 1/2 mv1 squared of course, kinetic energy of the second particle before is 0, and it is equal to 1 over 2 m v1 prime squared plus 1 over 2 m v2 prime squared. Okay, so two equations, and hoping that it will be enough. Right. So we can just deal with these two equations. Okay, masses, let's just brutally cancel. Mass, murdering, distraction, whatever, right? So obviously, in order to get something out of them, let's just square the first equation. Right, so probably I should label. So this is equation number 1, and this will be my equation number 2. So let me work with equation number 1. So it will be, of course, v1 squared equals to v1 primes plus v2 prime, of course, squared, and of course we will get v1 squared prime plus v2 prime squared, and plus 2v1 prime dotted with v2 prime. And sometimes it's useful not to open this up. And I think in your homework there will be also. It can be useful. So now compare with the second equation. Which is, of course, v1 squared equals to v1 prime squared plus v2 prime squared. So if we compare these two equations, we can see. Hold it. No, everything is good. I don't know why I started doubting myself. Something looked strange. No, everything is good. All right, so these sides the same, these are the same, these two terms. So it means that, and this is the extra term, which is missing over here. So it means that this must be 0, right? This must be 0. And of course, it must be 0 for any velocities v1 prime and v2 prime. All right? So v1 prime dotted with v2 prime must be equal to 0 because both of these laws are correct. And since, again, v1 prime and v2 prime can be any, so it means that angle must be 90 degrees all the time. Right? Since v1 prime and, no, not, let me write absolute value, and v2 prime since this velocity can have different values, right? Can have different values. Since we can have different values, right? So we can say that it's a cosine of theta equals to 0, and of course theta equals to pi over 2, right? Okay, so that's the basically a proof. And again, something similar will be in your homework. And again, I remember it's better to keep the dot product almost till the very end. I think it's if one mass is larger than the other one, so then the angle will be sort of larger than 90 degrees. In the other case, less than 90 degrees, right? But the idea is quite similar. Okay, so the last stretch. I raised that question at the end of the previous class. Okay, let me stand over here so that I wouldn't be blocking. When we discuss motion of this, for example, ball, right? And of course, what do we have? it is exposed to external force, which is a conservative force. Of course, we can introduce gravitational potential energy, blah, blah, and so on. But at the same time, it's a multi-particle system, this rigid object, rigid body. And of course, all that stuff which I erased, and now I feel like I wish it was in front of me, right? So it has tons of particles inside, right? Pairs of particles, right? They interact through usually what electrical forces and or gravitational forces, which are conservative, central, obey Newton's second law. So all that stuff can be used, right? Can be used, and of course we can introduce potential energies U as a function of a relative position vector. But actually it can be shown that it's also, we will do it when we get to central forces. It's not just a function of R1 minus R2, but it's a function of the absolute value of the relative position vector. Potential energy is a function of absolute value of R1 minus R2, right? And then what happens with the absolute value of the relative position vector, R1 minus R2? Of course, we can generalize R alpha minus R beta. What happens with that absolute value of the relative position vector as the rigid object moves? Particles in the rigid object are fixed, right, in space. So as a result, that R alpha minus R beta stays the same all the time. Right? Because we're not deforming the object, we're not doing anything weird, right? So as a result, all those potential energies are the function of some constants. So all those potential energies are going to be constants. And of course, you have gazillion number of particles, and of course, all those potential energies are constant. So if you add them up, the total, the net internal potential energy will be constant. And what can we do with the constant potential energy? We can trash it, right? We can ignore it. We can, by, for example, redefining the reference level for, you can just completely, because it will be on both sides if you use conservation of mechanical energy, right? It will be just on both sides of the equation. So any constant, you can just ignore it. Forget it. So that's why whenever we describe the motion of a rigid object, right, we can, which is exposed to a conservative force, external conservative force, we can completely ignore the internal potential energy. Okay, let me write a few sentences about this, right? And then I used to look at one example, some ball rolling on some surface, again, using conservation of mechanical energy. It's quite straightforward. So a couple of years ago, a year ago, I stopped looking at that. Right. And just somewhere in the middle of that example, which I'm sure that you've solved examples like this, I would just say, okay, you see, we have rigid object which rolls. It's some ball, right? Sphere. And at some point I would say, okay, you see, of course it has total some internal potential energy, but we're not going to include because it's constant, so we can just ignore. Right. Okay, I will move up here. So, yeah. Something short. Okay, let me put first rigid body. I'm just thinking a rigid body probably not enough in the title. So internal potential energy of a rigid object. Let me just suddenly I decided to change. Internal potential energy of a rigid body. Okay. Probably I need to change also in my notes the title. Okay, so of course it consists rigid object consists of n interacting particles. And of course they rigidly connected. That's why it is a rigid object. For example, I can draw some rigid object. I can take this particle alpha, yeah, and here, for example, beta. Right, so this will be defined by the position vector r alpha, r beta, right? And of course, we can introduce the relative position vector, like what I just in the we had or in this part which I just erased. Right, so this is r. Which way I labeled? No, I just wrote it. Okay, let me just write r alpha minus r beta. Relative position vector, right? Between two arbitrary particles in the rigid object, right? And okay, forces, central and conservative. F alpha beta and F beta alpha, of course, central, conservative, right? And of course, for these two particles, potential energy can be introduced, right? And I skipped this section. I moved it to the chapter where we're going to discuss central forces. I feel like it fits better there, where we will show that if the force is central and conservative, then it's spherically symmetric. So basically, as a result, instead of writing u as a function of r alpha minus r beta, I can put an absolute value. So basically, it's a function of a distance, not a vector, distance between interacting particles. So as a result, the u, which we labeled total internal potential energy consists of tons of these terms. Of u r alpha minus r beta. Again, I used to derive it I would go through all these summations, right, excluding that particle, and the next sum excluding that particle, right? And then last year I looked kind of, it's interesting, right, from the calculus point of view, but I think we can save time for something else by just me saying general in words and writing a few sentences and skipping all this derivation, right? So consists of all these particles, right? And this is basically a constant during a motion. Why constant? Because this distance, r alpha minus r beta, as particle, and on the particle rigid body, maybe it spins, right, flies, translational, rotational motion. But since we're not deforming an object, we're not distorting it, as a result, these r alpha minus r betas all stays the same. So it's a constant. And since it's this function of a constant, so of course, the whole potential energy term is constant, right? So as a result, if you add them all up, so this u total internal potential energy will be also a constant. All right, constant during the motion. So u total internal potential energy is constant. Constant and can be ignored because it will be on both sides of the conservation of mechanical energy and can be ignored. Right. So that's why we never discuss that in the problems. Right. Yeah, example, as I said, yeah, it's basically physics 1 example. Right. So sometimes I skip this in this or that section in Newtonian formalisms to save more time for the advanced part. Okay, that's the end of the energy chapter about energy, the end of chapter 4, right? And now let's move to chapter 5. So let me write. So the end. Okay, so chapter 5, it's reasonably long. It's all about oscillations, but oscillations of one object, one object. And coupled oscillations at the end of the semester. We will probably have maybe a couple of classes about coupled oscillations. Right? Here, no coupling. Right. So we're going to discuss basically a harmonic oscillator, right? Yeah, we'll write what that is. And it's one of the most ubiquitous systems, right? It doesn't matter where you work, sooner or later you will end up with modeling this or that using a harmonic oscillator, right? So that's why it's one of the fundamental parts in classical mechanics. Okay, so now let me write chapter 5, harmonic oscillator. Right. Again, we're going to discuss a single particle, one object. Okay, let me just write single particle. All right, so a single particle. Then, in order to have oscillations, that particle must be around which point? Of course, stable equilibrium point. Unstable, it will just run away and it will never come back. So it must be, so it moves around a stable equilibrium point. So moves around a stable equilibrium, right? So that's the second part. Then those movements, those oscillations must be small, right? Because we're going to use expansions. So small oscillations, we're going to make that assumption. So then small oscillations. Small oscillations, of course, around a stable equilibrium point, right? And that's what we call a harmonic oscillator. That's what harmonic oscillator is, right? So, and that's what we call, okay, now let me use different colors. So that's what harmonic oscillator. So we need to describe this system. Description of any system. Basically, I describe the motion, right? So what can be used? Of course, we can use what? Either force approach based on Newton's second law, or we can use energy approach, which we just recently developed, right? This time, we're going to use the very foundation, Newton's second law, right? And in order to apply Newton's second law, of course, we need to sort of model, describe interaction of a system with an object which exerts a force, right? And because which exerts a restoring force, so that our system can oscillate. So we need to describe that interaction somehow, right? Because yeah, of course I know, and you know that Hooke's law, but we need to get it naturally, more or less, right? So we need to introduce that interaction first, and only then, when we introduce the Hooke's law, right, only then we can grab that interaction and use it in the Newton's second law. So first, a few minutes, we need to introduce the interactions. Right? Okay, and then, of course, yeah, we'll just Newton's second law, and we'll start solving it, that differential equation. But before we start using calculus, let's just discuss some physics. Okay, so let's assume that we have a system, an arbitrary system, conservative. Okay, let me put a new bullet. Okay, so now I'm thinking, should I label it sort of, let's introduce interactions? No, okay. I need to think properly sort of that title, maybe. I'm just coming up with my own titles, not like in a book, right? So consider a, as I said, conservative system. What else? Okay, so consider a conservative system. You know what? An arbitrary, let me emphasize, an arbitrary conservative system, basically any conservative system. Conservative system. So, system is conservative, of course. We can plot potential energy versus position. For example, completely, again, as I said, arbitrary. Let me use some different color. Right? So let's say potential energy. Just drew something. And so now, of course, for any conservative system, right, for any, okay, not for any, but if you if you find the minimum point, in this case, you can pick this point. Of course, I will pick this one, right? So stable equilibrium point, right? And let me position coordinate system over there, right? So maybe let me do it like this. So this is X. This is y, and that was point x naught, but of course x naught in this case, since I position my origin at that point, so it's 0, x naught equals 0. Right? And so now we assume that system is here. Right? Now, and since we are going to assume that we have small displacements, right? So we can use Taylor expansions. Right? So let's expand this potential energy. Okay, let me emphasize. So this is u as a function of x, potential energy as a function of x. Let's expand it using Taylor expansions, right? So small oscillations. So we're using these small oscillations. So as a result, we can use Taylor expansions. Right. Okay, I should be able to fit it. So what, u as a function of x approximately equal. Of course, it will be u as a function. Okay, let me you write. So x naught equals 0. And of course, that is the stable equilibrium point. Right. So we use this. Now we're using that. Right. So around 0, because I position origin there, plus u prime at 0 times x, and plus 1 over 2 u double prime at 0 times x squared. And of course, plus blah, blah, blah. Okay, so this u at 0, some constant. So can be ignored, like we ignored over here mechanical potential energy, internal potential energy, because it's constant. Then it's a stable equilibrium point, so as a result, this is 0. It's a stationary point. Stationary point. And we cannot say much about that for now. But it's obviously, not obviously, it is constant, right? Because, yeah, you differentiated it twice, evaluated function at a certain point. Of course, it's some number, right? And, of course, who wants to deal with u double prime, right? So it's too complicated to write. Let's just rename it. Let's denote that as k, right? So let's denote as k, 3 lines, u double prime at 0. And we can call it spring constant. It's sort of, the term is kind of attached to the spring mass system, right? It's better to call it force constant. Force constant. All right, so let me check if I mentioned everything which I was planning. Right. Okay, anyway, so force constant. Force, you know what, I want to leave this space. Let me write underneath. Right. So this is a force constant. Right. Of course, we need to frame it, right? Because it's very important. Remember, if you have a potential, if you differentiate it twice and evaluate at around stable equilibrium point, that's the force constant. And so now, what else do we have to impose on this k, right? So second derivative must be positive in order to have minimum point. So in this case, in order to have stable equilibrium point. So we can have oscillations only when k is positive. Because again, if k is negative, second derivative is negative, it means that you are at the maximum point. Yeah, it's still stationary point, but unstable point. So in order to have oscillations, k, force constant, must be positive. Right. Okay, let me write something about this. Right. So k, I still want to save that space for another picture. So k must be positive. You know what? Let me write k equals to u double prime. And then must be positive, right? Only in this case we can have oscillations. Oscillations are possible. Right. So k must be positive. And as a result, of course, we can write potential energy equals, okay, just rewriting this 1 over 2 k x squared. So basically, Hooke's law, right, written in the form of potential energy. Usually, for after high school, students remember just force equals minus kx, but it's also Hooke's law. Right. Without E, I think, yeah. Hooke's law. Okay, so it's a parabola. Basically what? We just cut these ends, right? And we assume that our potential energy around the stable equilibrium point is just a parabola. Right? It's just a parabola. And that's why I was trying to save some space, but still with this writing I invaded that part. Okay, I hope you wrote it down, so let me erase this. Right. Okay, so with our modeling, so basically what we're getting, right? So this is x, this is u. Actually, yeah, you can use u, you can use energy, it's not a big deal. And of course, now we model this part, right, in the form of a parabola. Right. So basically, right. And now we can use what? The second remarkable feature, it's a one-dimensional system, right? One-dimensional system, and right now we're looking at that from the energy approach, right? Of course, then in 5 minutes I will start writing down Newton's second law and using that. But for now, yeah, we can use the second remarkable feature. So of course, over here, if the object at this point, right, so the force will be that way, restoring. If an object at this point, so the force will be restoring, driving it back. Again, slope is positive, but because minus in front, so you can get this direction. Then if you provide, let's say, this amount of total mechanical energy, let's say E, let's say this. So this will be a turning point. This will be a turning point, right? So turning points. So the areas of existence only between this minus A, which is amplitude, and this A. So over here, system cannot be, because in this case, potential energy will be larger than total mechanical energy, which means kinetic energy is negative, which is of course impossible, right? So that's where the system can be. So the system can oscillate between minus A and A, right? And so you can, yeah, you can look at this as a, I don't know, like a roller coaster track. You remember when we discussed the second remarkable feature? All those tools can be applied here. So what else? Okay, so and now generalization. Since you see on purpose, you remember I stopped and I wrote arbitrary system. So basically we pick a completely arbitrary system and discuss the potential energy. So basically it means that general validity of Hooke's law of this formula, right? So you can pick any system, conservative system, find any stable equilibrium point, and use that. Any system, conservative, of course, right? And use that, this Hooke's law. It's called general validity of Hooke's law. Right. But of course, K can be different, right? We will look at the examples, right? K will be different, right? Right. Since we used an arbitrary system, right? So we can say about general validity of Hooke's law. So let me write, just use my notes. Hooke's law is valid for any potential energy function around a stable equilibrium point. Right, so Hooke's law is valid for any potential energy around a stable equilibrium point. General validity of Hooke's law. Okay, so now, since we're going to use Newton's second law, let's just make a quick transition to the force, and we know how to move back and forth between the potential energy and the forces, right? So let's do that. Look at the example. quickly and call it a day. So I thought I will be able to start solving that differential equation, but it looks like it's not. All right. So, of course, transition to the forces, right? F equals minus gradient of u, right? But we have one-dimensional system, so of course it can be simplified. Right? So it will be f, okay, everything happens around x, so fx equals to minus partial derivative with respect to x of 1 over 2 kx squared. Right. So it will be minus kx. Right. So of course, everyone knows that, right? So minus kx, and again, this is also called Hooke. Again, why did I use E? Hooke's law, right? And of course, that's what we're going to use in our Newton's second law. And actually, we can also justify by looking at this looking at this expression why k must be positive. Why k must be positive? Let me quickly do that. Right. So if I plot, not plot, draw. Let's say this is x, and let's assume that we have a mass spring system. First, it is compressed. Let's say this is equilibrium. Let me draw this green. So x, and let's say over here it's an equilibrium point. Right, so that is x equals to 0. Okay, in this case, x is negative. X is negative position of this mass right now. So if x is negative, minus in front, minus and minus give us plus. And if k is positive, so force will be positive. So in this case, force positive, giving us that direction, the needed direction, restoring force, right? So in this case, force will be acting this way, right? So if k is positive. But now let's displace our system to the other side of the equilibrium. Right, so over here, let's say our mass is over here. Right. So now, of course, x is positive. X is positive. It's a positive. If k is positive, minus in front, so the force is negative. Again, force is a vector, so negative force means it points in the negative x direction, right? Right. So again, these forces happens if k is positive. If k is negative, of course, in that case, system is not going to be oscillate. If you displace it, force will just drag it away from the stable equilibrium, from the equilibrium point. Right. So let me write something like this. So if k is positive, then F is a restoring force. Right. And of course, if k is negative, then it's an unstable system. Unstable system. Then this force will just drag the system away from the stationary point. Right? And another thing, quickly, just to again connect this with results which we got before. It's a one-dimensional system, right? And the force is a function of x only. So we can recall that first remarkable feature, which allows us to check if a force is a conservative force. You remember? So the first condition, if the first condition is correct, which is the force is a function of position only. If the first condition is correct, the second condition is automatically satisfied, and we can call that force a conservative force. Our force is a function of position only x, so it's a conservative force, and of course we can introduce potential energy, right? So, which is here, but we moved in the opposite direction. Okay, so that's what I wanted to tell about sort of this interaction, right, which we needed to discuss, introduce. So we introduced this Hooke's law. And now, basically, we are ready to describe the system, again, using Newton's second law. But before we will do that in a week, on Thursday, I want to look at one example, which you remember that cube rocking on the cylindrical surface. Right? We wrote down the potential energy, right? So I want to get this form. We wrote down that potential energy not just for small oscillations. We wrote down that potential energy without any restrictions. Any oscillations, any displacements are possible in that potential energy. So basically we need to grab that potential energy, expand it like what we've done here. And I want to get Hooke's law. Again, just to emphasize that on general validity of Hooke's law, you can use any conservative system. If you plot potential energy, find the stationary point, and you can use Hooke's law, and you can have a harmonic oscillator, and you can have an oscillations around that stable equilibrium point. So next class we will start from that. We will just get K and see the same results. We'll get the same results as we got a couple of classes ago. And then just Newton's second law, and then we will solve the differential equation and start looking at all possible situations, all possible solutions, which are good, which are not good, advantages, disadvantages. And then we'll start making system more complicated. So first we will add drag forces, then driving forces, and every time solving the differential equation. Right? It's more like a calculus. Okay, so that will be next. And after this chapter, after chapter 5, we will start moving to the Lagrangian formulas. We will look at the calculus of variations and then Lagrangian formulas. Okay, that's it for today.
Broadly in the sky, the sun shines like a pearl. Metal